All right. Good morning, everybody. So today let's finish what we started talking about concentration, and then we will move on to oxidation numbers. Okay. So before we start talking about concentration, let me just recap one thing to make sure we are all in the same page. Okay, so it may happen sometimes when you have more than one hydrogen atom in an acid structure. So we didn't go over the strength of acids. So here we are going to consider that all acids are strong acids and they are going to lose all the hydrogens. Okay, so for example, here H3PO4, technically you can lose one hydrogen each time. So you lose one hydrogen first, then you form this H2PO4 minus structure, then you may lose another one and then another one. Okay, so step by step. To make things simpler here, we're going to consider that all the hydrogens are lost and the three hydrogens in the structure in the water are going to produce 3H plus ions, okay? And remember, the number here indicates the amount of hydrogens in the structure. So therefore, the index becomes the stoichiometric coefficient in the product side. So it's not correct to represent something like that because that's telling us that we are forming a structure with this shape here, which is not correct, okay? So what we are forming is 3H plus ions, okay? So therefore, the index becomes the stoichiometric coefficient. All right, okay. So let's go back here to concentration. So I showed you on Monday the formula. So very simple formula. So let's do here a quick recap about the equation. There are two ways to represent concentration. The first one is called molar concentration and the units mole per liter. And the formula is the one showed on the left side. So here N is the number of moles. Oops. And V is volume. Units here, number of moles has to be in mole, volume in liter. Therefore, the molar concentration is mole per liter, or sometimes is represented by an uppercase M, meaning molar. Okay. Another way to express concentration is mass per volume. Okay. And the formula here is the one represented on the right side of the slide. And in this case, concentration is going to be mass divided by volume. In the international system, mass is in kilograms. And then here for volume, we are going to use the usual unit volume. Therefore, concentration is going to be in kilograms per liter. So when are you going to use molar concentration and when are you going to use the concentration in kilograms per liter? Whatever the exercise asks you to do, then that will guide you regarding which formula to use.
George, do you mind scrolling down? It's hard that the Zoom bar is in the way. Thank you.
Okay. Thank you for telling me. Okay, so uh, just remember, you can calculate the concentration of anything that is in solution, okay? So, and here, pay attention that molar concentration requires to be number of moles divided by volume. If I give you the mass of a compound or an atom and ask for the molar concentration, you will have to first convert mass to number of moles and then input in the equation. Okay, just attention to that detail. Okay, so now I want to move on to dilutions. Okay, so dilution by definition means to decrease the concentration. Okay, so every time you dilute a solution, it means you aim to decrease the concentration of this solution. So let's start here with a very simple example, and then let's talk about dilution. So imagine here that I have a sodium chloride solution. The initial volume of this solution is 0.5 liters, and the concentration of this solution is 2 mole per liter. Okay, so we have here a stock solution of sodium chloride, concentration 2 mole per liter, and volume is 0.5 liters. So we are going to assume here that sodium chloride is evenly distributed throughout the solution. And for some reason, we want to obtain a sodium chloride solution with the concentration of 0.1 mole per liter, starting from our stock solution. So here the question is, what is the final volume of the solution? So see here that I'm decreasing the concentration. So that means now we have the same amount of material dispersed in a larger volume. Therefore, every time you dilute a solution, we are just increasing the volume, okay? And the amount that the volume is increased, that will depend on which final concentration we want to achieve. In the case of the dilutions, we can use a very simple formula that will tell us what's the final volume or what's the final concentration. So we are going to use C1 times V1 equals to C2 times V2. C1 is the initial concentration. V1 is the initial volume. And on the right side of the equation, we have final concentration and final volume. Okay, so every time we dilute, we are just adding solvent. So the number of moles is still the same, So by adding volume, we decrease the concentration and therefore we dilute. In a dilution process, the product initial concentration by initial volume has to be equals to the product between final concentration and final volume. So let's go back to our problem here. We have a solution with initial concentration 2 mol per liter and initial volume 0.5 liters. At the end, we need to obtain a solution with a concentration of 0.1 mol per liter. And our goal is to calculate the final volume here. So let's call it V2. Okay, so that's how you set up a dilution problem. And then just doing the whole math here, the final volume is equals to 10 liters. Okay. So therefore, if we start with a 0.5 liter stock solution with concentration 2 mol per liter, to obtain a 0.1 mol per liter solution, we have to increase the volume all the way to 10 liters. So you are always going to start with a more concentrated solution and dilute to a less concentrated solution. Pay attention to the units. All the units on the left side, they must be the same as the units on the right side of the equation. Okay, so that's everything I want to talk with you about concentration. Remember, we can calculate the concentration of anything that is in solution. Every time we dilute a solution, we are starting from a higher concentration and going towards a lower concentration. So dilution always means to decrease the concentration. We are going to assume here that the molecules or the ions are evenly dispersed in the solution. So every time you dilute, you just add more solvent. So now you spread out the ions more in the solution, which means you decrease the concentration. Okay, so very good. So now I would like to move on to oxidation reduction reactions. And we are going to start talking about oxidation numbers. So let me quickly change my screen here. Okay, so very good. Oxidation reduction reactions. So if we have here a nice strip of magnesium and we light this strip on fire, the magnesium will react with oxygen. This is here basically a combustion reaction. And this reaction will produce magnesium oxide and emit a very bright white light. Okay, so we are starting here with magnesium solid reacting with oxygen in the gas state, forming a new compound. Any chemical reaction involves the transfer of electrons. Okay, so we are going to rearrange the atoms and also transfer electrons from one species to another species. Electrons cannot be created or destructed, only transferred. Attention with that. Okay, so if someone is losing electrons, someone is gaining electrons. And always remember that an element that lost electrons becomes positive, while an element that gains electrons become negative. So you already know a little bit about that because we studied a little bit ionic bonding. And you remember that in an ionic bonding, there is an element that loses electrons and another element that will gain electron. Okay, so it's basically a transfer of electrons. Okay, the oxidation number ON, or oxidation state of an element, gives us an idea of how many electrons this element lost or gained. Okay, so the oxidation number is a quantitative way to determine or to have an idea how many electrons an element lost or how many electrons an element gained after being bonded to other elements. And here we are going to follow the same idea that we did for charges. An oxidation number negative means that the element gained electrons. So therefore, we have an excess of negative charges. On the other hand, an oxidation number that is positive means that this element, after the bonding, lost electrons. And therefore, there is an excess of positive charges. Okay, so the idea here is that in a chemical bond, there is always a battle for the electrons. Okay, some elements, they like or they pull the electrons with more strength compared with other elements. And this is a property of each element that we are going to tackle later on, called electronegativity. Some elements have the ability to attract more the electrons compared to other elements. So imagine here, every time there is a chemical bond, there is a fight for the electrons. Some elements will pull stronger than other ones. To determine the oxidation number of any element in a compound, there is a set of rules that we are going to tackle right now. Okay, so first rule, each atom in a pure element has an oxidation number of 0. So that means any compound that's formed by just one element, the oxidation number of the element is 0. For example, bromine bonded to bromine, this falls in the first case, and that means the oxidation number of each bromine is 0. So when you have bromine bonded to bromine, there is a sharing of, oops, sorry about that here. Let me change my screen. Okay, so bromine bonded to bromine, they are sharing one pair of electrons, and I'm going to represent here each electron by a dot. And each atom, because they are identical, they will pull the pair of electrons with the same strength, which means the pair of electrons is going to be right in the middle, meaning that nobody gained and nobody lost electrons in this case. So therefore, the oxidation number for each bromine is 0. Okay, so the meaning of that is that nobody lost and nobody gained electrons. We have a perfect sharing of electrons here. Okay, second rule, the sum of the oxidation number of the atoms in a neutral molecule is 0, unless the ion is charged. So let's tackle here two examples. First one is CO2. The charge of the molecule is always the number on the right upper corner. If there is no number here, that means the charge is 0. Therefore, this is a neutral molecule, which means that the sum of the oxidation numbers of all the elements in this compound has to be 0. So every time we have a neutral molecule, if we add all the oxidation numbers for all the atoms in the compound, this has to be 0. However, if there is a charge, for example here carbonate, there is a charge of 2 minus, that means the sum of the oxidation numbers has to be the charge of the ion. So in this case, 2 minus, because that is the charge. Okay, so be careful when we have a neutral molecule and a charged ion. In the case of the neutral molecule, the sum of all the oxidation numbers for each atom has to be equal to 0. When you have a charge, the sum of the oxidation numbers for each atom has to be equals to the charge of the ion. Okay, rule number 3. Hydrogen is so weak that the oxidation number of hydrogen is, in most cases, 1 plus. The only exception is when hydrogen is bonded to a metal, and then in this case, the oxidation number of hydrogen is 1 minus. Okay, so metal here is going to be any element from groups 1, 2, all the way to the group 13. Okay, so hydrogen is very weak, therefore the oxidation number is in most of the cases 1 plus. The exception is when hydrogen is bonded to an element from groups 1, 2, all the way to the group 13. So in this case, the oxidation number of hydrogen is 1 minus. Okay, so the goal here is usually to find the oxidation number of one of the elements in the compound. So let's see here the example for HCl. First thing, HCl is a neutral compound. How do I know that is neutral? Because there is no charge here on the right upper corner of the molecule. If the compound is neutral, that means the sum of the oxidation numbers for all the atoms has to be 0. So let's rewrite here HCl, and I'm going to put here a 0 just to indicate that the sum of the oxidation numbers is 0. So we are going to equal the sum to 0. Now we have hydrogen in the structure of the compound, and chlorine is not a metal. Therefore, we know that the oxidation number for hydrogen has to be 1 plus. The other element in the compound is chlorine. So let's add the oxidation number for chlorine right here. And we know that the sum of all the oxidation numbers has to be 0. Therefore, the only possible oxidation number for chlorine in this compound is -1 or 1 minus. What is the physical meaning of chlorine having an oxidation number equals to 1 minus? It means that in the compound HCl, the electrons are closer to the chlorine than the hydrogen. So if we were able to take a picture of the electrons in this compound, I'm going to represent here the electrons by black dots. So the pair of electrons being shared would be closer to the chlorine than the hydrogen. So that's why chlorine has an oxidation number of 1 minus and hydrogen 1 plus. Okay, so that is the physical meaning of oxidation numbers. Okay, so let's take a look now at rule number 4. The oxidation number of oxygen is usually 2 minus, except when peroxide compounds, in peroxide compounds where it is 1 minus. Okay, so oxygen is so strong that in most of the cases, its oxidation number is going to be 2 minus. The exception here is when we have a peroxide compound, and peroxides are defined by compounds that have oxygen bonded to oxygen. So I don't want you to worry about the exception because I will not cover here. Let's deal with the most of the cases when the oxidation number of oxygen is 2 minus. So let me give you an example. So we have here the compound CO2. So we are always looking for the oxidation number of one of the elements in the compound. So we know that oxygen has usually oxidation number of 2 minus, and what we are looking for to determine is the oxidation number for the carbon in this case. First thing that I have to look at is the charge of the compound. If there is no number on the right upper corner, that means the compound is neutral. And therefore, the sum of the oxidation numbers has to be 0. Okay, so let me do the same thing that I did before. So we have here CO2, and I'm going to write 0 here just to make things a little bit easier. Because the compound is neutral, the sum of the oxidation numbers has to be 0. We know that the oxygen is so strong that the oxidation number for this element in a compound is usually going to be 2 minus. So let's write here -2 for the oxygen. And here, just adjust one thing here. -2. And here, pay attention to one thing. Because we have 2 atoms of oxygen in the structure, we have to multiply by 2, because the oxidation number for each oxygen is 2 minus. If you have 2, as indicated by the index here, you must multiply the oxidation number by 2. And our goal here is to determine the oxidation number for carbon. The compound is neutral, therefore the oxidation number of the carbon plus 2 times the oxidation number for the oxygen has to be equals to 0. Therefore, the only possibility for the oxidation number of the carbon is +4 or 4 plus, okay? Whatever you want to use to indicate the oxidation number is fine with me.
George, can you explain why you multiplied by 2 one more time?
Yes, because see here, CO2, the index here after the oxygen indicates that we have 2 oxygens in the structure, okay? So the oxidation number of 2 minus is for each oxygen in the structure. So if we have 2 oxygens in the structure, then we have to add here the 2, okay?
Thank you.
No problem. So remember that the oxidation number is going to be multiplied by the number of atoms in the compound. And that's why I multiplied by 2. Okay, so the physical meaning of an oxidation number of 4 plus for the carbon is that in this compound, carbon basically lost 4 electrons. Or in other words, the electrons are closer to the oxygen than the carbon. So again, if we could take a picture of the electrons in the compound, here doesn't matter how many electrons are being shared between carbon and oxygen, they would be closer to the oxygen than the carbon, okay? So that's the meaning of a negative and positive oxidation number. Okay, so here the goal is always going to be the determination of the oxidation number of one of the elements in the structure of the compound. So there is a set of rules that will help you to gauge some information at the beginning to set up the problem, and then you always will end up with some one thing that you don't know and you can find it. Okay, so rule number 5, fluorine is the strongest of the element and has always oxidation number equals to 1 minus in any compound. The only exception is when fluorine is bonded to fluorine. Therefore, in this case, the oxidation number is going to be equals to 0 because the strength that they pull is the same. Okay. For all the other cases, fluorine has oxidation number equal to 1 minus. So the example that I want to show you is for the CF4 compound. So again, we know that the fluorine has oxidation number equals to 1 minus in any compound except F2. We know that this compound is neutral. So the goal here is to determine the oxidation number of carbon. So let's write all this information. So there is no charge for the compound, meaning this is a neutral compound. Therefore, the sum of all the oxidation numbers for all the atoms is 0. So let me do the same thing I did before. Let's write the compound. Let's write 0 here just to make things easier. So compound is neutral, therefore the sum of the oxidation numbers is 0. Oxidation number for fluorine is going to be -1 or 1 minus. Again, we have 4 atoms of fluorine in the structure of the compound, meaning we must multiply each oxidation number by 4. And the goal is to determine the oxidation number for carbon. So therefore, the only possibility for the oxidation number of the carbon is +4 or 4 plus. The physical meaning of an oxidation number of 4 plus for the carbon is that carbon, when combined with 4 atoms of fluorine, is going to lose 4 electrons. Or, in better words, the electrons are going to be closer to the fluorine atom than the carbon atom. And again, if we could take a picture of each chemical bond between carbon and fluorine, the electrons are going to be closer to the fluorine atom than the carbon atom. So that's the meaning of a negative oxidation number and a positive oxidation number. And finally, rule number 6, the last one. Elements from the group 1, when combined, have oxidation number 1 plus in all cases, and elements from the group 2, when combined, have oxidation number 2 plus. Elements from group 1 are so weak that they, in almost all the cases, will have oxidation number 1 plus. And the same for group 2. They are so weak that when combined with other elements, they will have oxidation number 2 plus. Okay, so with the 6 rules that I showed you, you are going to be able to calculate the oxidation number of any element in any sort of compound. And that's our goal for oxidation numbers. And what you will have to solve is something similar to this example here, okay? So I'm going to ask you to determine the oxidation number of the elements in bold. So in the first case, we have ClO2, and I'm asking you the oxidation number of chlorine. The second case, we have ClO4 minus. So minus is the charge of the ion, and again, oxidation number of chlorine. And the third case, we have SO4 2 minus, the sulfate ion. 2 minus is the charge of the ion. And I'm asking you to find the oxidation number for sulfur. Remember that the meaning of the oxidation number is that the electrons are close to one element when it is negative, or far from this element when it is positive. So we will not have time to tackle this example right now. So I will ask you to think about it and try to do by yourself, and then we will go over it on Monday. Okay, so Friday we will have in-class assignment. I will be available here during the period if you have any sort of questions. With that, I will finish at this point, and I will see you on Friday.
Thanks, George. Have a great day.